Hello, my name is Paulo Passos and I will be presenting this paper called a three-phase multi-level AC-DC converter operating as a shunt active power filter. As we can see, the adopted topology is a three-phase cascade full bridge converter, which is able to generate 5 different levels with 6 different states. Each phase has 2 different DC submodules. With the use of multi-level converters, it is possible to generate more output voltage levels. And the more levels produced, the better is the quality of the output voltage, having less harmonic distortion. Also, there is a reduction of the dVdt, which allows a reduction of the switching frequency, reducing the switching losses. Considering that there are two independent DC links per converter, 2 P controllers are implemented, one for each DC link. Each of them works either in the positive semi-cycle or in the negative semi-cycle of the grid voltage. This slide presents the control algorithm applied, and each DC bus has an independent PI controller, which allows the DC bus to be loaded separately using the applied PWM modulation level shifting, which is presented at the image in the bottom left. The PWM modulation uses 2 modified sinusoidal waves to allow the individual control of the DC links. The top left image presents the control diagram block. It starts by calculating the necessary power to properly control the DC links. It is then applied the FPD power theory, which allows to calculate the grid current reference, resulting a PLL because the grid voltage can be distorted. The top right image presents 5 different levels produced by the converter as well as its reference, which results from the output of the control algorithm. Last, the bottom right figure presents the different pulses which are applied to the semiconductors in order to be able to generate the 5 output levels. In order to validate this topology, the software tool PowerSim was used. The grid voltage was emulated to provide a real scenario. This means that harmonics were introduced in order to get around 4% of THD percentage on the voltage, as in a real life case. The bottom image presents the grid current values when all the loads are connected. The connected loads are a single phase rectifier per phase with an RC filter, 1 RL load per phase and 1 R load per phase. These loads were selected, taking into consideration what real industrial loads will be. Here it is presented on the top image the compensation currents calculated by the control algorithm. The compensation currents produced by the shunt active power filter are not going to be symmetrical with the current consumed by the loads, since the DC link needs to be kept balanced, allowing the power grid to only provide the active power needed by the loads. With these compensation currents, it is possible to achieve sinusoidal grid currents as well as lower the THD of the current. We can observe that the THD of current dropped around 30% in each phase. In this new scenario, we aim to validate that the active power filter can compensate for the load's current in a transitory situation. In order to perform this validation, only the non-harmonic loads are connected to the converter, which means that only the DC link is being controlled. Then, the harmonic loads are connected to the converter with the goal to verify if the active power filter can properly calculate the compensation currents and reduce the harmonic distortion of the currents. We can observe that the filter starts operating at 0.1 seconds, which is the moment that the loads are connected. This image presents the voltage output waveform of each of the converters that compose this three-phase system. It is possible to observe at 0.1 seconds the moment when the harmonic loads are connected, because the DC link sinks for a short moment and then recovers as the filter starts compensating. This validates the correct operation of the multi-level converter, since all the levels are correctly produced. In the industrial context, a large amount of the applied loads are characterized by a nonlinear behavior. This means that the current consumed presents harmonic distortion, deteriorating the power quality. Additional, low power factor and unbalances are also critical power quality problems that are presented in the industry. As a contribution to mitigate these problems, this paper proposes a three-level multi-level AC-DC converter with 5 different levels operating as a shunt active power filter, considering the industrial environment. Due to the fact that this converter can operate with 5 voltage levels, it can reduce even more the THD values of the power grid when compared to other traditional topologies with fewer levels. The ADAPT multi-level AC-DC converter was validated in 2 different situations, in a steady state situation and in a transient state situation. By analyzing the obtained results, it is possible to observe that the THD of the current value of each phase dropped around 34% to approximately 4%, while the THD of the voltage has a value of around 4%. Even though the THD of the current is still at 4%, the obtained power factor was almost unitary. When compared to traditional topologies that produce fewer levels, although it applies more semiconductors, the semiconductors are not exposed to such high DVDT, which is beneficial since it allows the application of semiconductors with a lower voltage rating. I want to thank the FCT for supporting this project, and I want to thank everyone that took the time to watch this presentation. Thank you.